Welcome to our first of two videos on models for text classification. We'll work through a couple implementations for classifying documents in the 20 newsgroup dataset. We'll also dive a little bit deeper into subtleties that can arise when working with RNNs in TensorFlow. We'll start with a brief overview of the 20 newsgroup dataset, which we'll be using to train our models for the remainder of section 3. We'll then spend some time going over the process of converting a text dataset to TF records format, which can then be processed efficiently by a TF record dataset object. For the rest of the video, we'll be implementing our model, which you've seen most of the code for already, and then we'll be training and evaluating its performance. The 20 newsgroup dataset contains just under 20,000 documents total, 11,293 training samples, and 7,528 test samples. Each sample consists of a document and its label, which can be one of the 20 possible labels shown in the table on the slide. Our goal is to be able to train a model such that, given any news document belonging to one of these 20 categories, it can reliably determine the correct category. Today we're going to dive right into code, so let's get to it. We'll be working with the same main function and general layout as we've seen in the previous videos for section 3. Here we do our setup. We've already gone through this exact code before, but today I want to spend a little bit more time on the TF records conversion, the conversion from our text 20 newsgroup dataset into a format that TF records dataset can process and handle. So remember that at the end of our processing pipeline, we had saved TF records from the TF records util file. So let's walk through the implementation of that and give an overview of how TF records works in general. We begin by converting our sequence of text into sequence of token IDs. That's what this vectorized function here does. But what we're going to focus on is this block here where we write our data into TF records format. In most cases, we create our TF record writer and then enter a loop iterating over each data sample. For us, a data sample consists of a string label and a list of integer token IDs. The way you format data to be saved in TF records format is you place it in a tf.train.example, as we've done on line 76 here. The constructor for the example takes a dictionary of features. The keys for this dictionary are strings representing the name of each feature, which we are free to decide. I've decided to associate my labels with the word label and my token IDs with the word sequence. A small detail to notice is that a feature is defined as being either a list of floats, a list of integers, or a list of bytes. Notice how all these options are lists, which is why I had to insert my label as a single element list as shown. After you wrap your data inside the tf.train.example, all that's left is calling writer.write on the serialized example. We've left out one key point, the implementation of the toFeatures function, which is doing all the heavy lifting for us. So let's go and see how that works. As mentioned, a tf.train.features object is just a map from string to a feature object. To emphasize, there are two distinct objects that I just mentioned. A features object, plural, whose values are individual feature, singular, objects. With that said, notice a pattern emerging here in the return statement. We create the features object by calling its constructor and passing in feature equals features. Also, there's some weird plurality differences. Even though we're passing in a multitude of features, TensorFlow has this name keyword as feature, which is a little strange, but not a big deal. But this has a very similar feel to how we created our tf.train.example object. And if we move up to the implementation for toFeature, we'll see the same pattern. It checks the type of values passed in and uses that to determine whether to instantiate the feature object with an int list, a float list, or a byte list. Note that we can easily convert string lists to bytes lists as shown here. And that's it, the end of the rabbit hole. I encourage you to read through this file and the corresponding example.proto file linked in the additional resources slide until you feel comfortable converting your data into TF records format. Now let's see how we actually read the data in with a TF records dataset object. As a review, remember that after we save our TF records, we create our classifier and pass it the usual arguments. Next, I've added something a little different than what we've seen before, a simple training and evaluation loop. This is one way of training for a fixed number of steps, then running the evaluation on the test set for a fixed number of steps, and repeating for some specified number of iterations. Now let's see how we read in the TF records data into our text classification model. That's going to be in our input function. Just as in previous videos, we have our input function call a helper dataset class's makeBatch function, where I've also added support for specifying whether we want the train or test dataset. So this is makeBatch. We first create the TF records dataset by passing it the path to our TF records file. Note that although the parameter for its constructor is called file names, we can also just pass a single file name if we're only using one file, which we are, either the training file or the test file. Now the process of reading the data happens here when we call dataset.map. Right now, each entry in our dataset is just a binary serialized TF records example exactly how we saved it. We now need to unserialize each entry. Our parser function is responsible for telling the dataset how to do this for a given entry. We use TensorFlow's parse single example utility to extract the features object, which recall is just a map from our string names to our feature objects. We pass it the serialized example, and we also need to specify the format to parse this example into. By format, I essentially just mean shape of each object, and we can do this with the fixed length feature or var length feature object depending on our kind of data. For the label, we know that's just a single string, whose shape we can always represent as an empty list. That's what you do when you have, in TensorFlow, something like a single integer or single float, single string. Its shape is just the empty list, or empty tuple. And we use the var length feature to allow for variable length sequences, since we don't know beforehand the length of each individual example. A quick post-processing step is converting the returned features from sparse to dense tensors, since var length feature will return what are called sparse tensor objects. We won't go into the details of TensorFlow sparse tensor objects, but just take that this is how you convert back to a regular tensor. We now have our label and sequence tensor pair, which is ready to be batched and fed to a model. Note that for batching our data, we use TensorFlow's padded batch method, which will ensure that each batch's sequence examples have the same length, given by args.maxSequenceLength, which we can specify at the command line. The padded shapes given are the shapes of a single example pair, the first being the sequence of tokens and the second being the string label. Finally, before returning, we convert the batch of labels to integer IDs using an index table, similar to how we used an index table in the embeddings video. Now let's move back to our model function. As mentioned earlier, you've actually seen most of the code for this model. We embed using the same code from the embeddings video, which we fed to simple LSTM cell and dynamic RNN, which we saw in the previous video. This is then projected to the number of possible classes, which for us is 20, and from there we build to our model's predictions, or we build the training nodes to obtain our train-op. If we scroll down, we'll see a new addition, the mention of the eval mode, which is the mode given when we run our estimator's evaluate method. All that's required is returning an estimator spec with the mode and loss, but typically we'll also want to pass an eval metric ops dictionary, since we are evaluating. The easiest way to do this is by using the functions from tf.metrics, since they're going to return the format expected by eval metric ops. I've chosen to include our prediction accuracy as one example case. And that's it. Today was more of a review of combining the code we've progressively built, as well as taking a close at TF records. The model itself will get much more complicated in the next video. As always, make sure to read the links here for an in-depth look at the topics covered today. Coming up next is the second part of our models for text classification video, where we're going to dive into more of the more complicated architectures that we described conceptually in the previous video. See you next time.